There is a profound stillness that settles over the world when the sun dips below the horizon and the last hues of twilight fade into a deep, velvety blue. If you find yourself far away from the glow of city lights, out where the air is clear and the silence is heavy, the night sky opens up like a vast, glittering cathedral. It is a sight that has captivated the human imagination since we first learned to look upward. We see thousands of points of light, each one a burning sun, each one a potential anchor for worlds we can scarcely imagine. The sheer beauty of it is enough to make us feel small, but it also invites a question that haunts us, a question that echoes through the corridors of our observatories and the quiet thoughts of anyone who has ever stared into the abyss. Is there anyone else out there looking back? When we look at the numbers, the universe seems to be teeming with possibility. Our own galaxy, the Milky Way, is a swirling river of stars, a disk of light and dust that stretches across 100,000 light years. It contains anywhere from 100 billion to 400 billion stars, and that is just one island in a cosmic ocean. Beyond the edges of our home galaxy, across the unimaginable voids of intergalactic space, there are other galaxies, not just a few, but trillions of them. The Hubble Space Telescope has peered into tiny patches of darkness, regions of the sky that appear empty to the naked eye, and revealed thousands of galaxies, each one filled with its own billions of stars. The numbers are so large that they defy comprehension. In a universe so vast, so ancient, and so rich with energy and matter, it seems almost impossible that we could be the only ones here. Logic tells us that we should not be special. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, are the most common elements in the universe, forged in the hearts of dying stars and scattered across the cosmos like seeds. We know that planets are common. Almost every star we study seems to have a family of worlds orbiting it. Some are gas giants, swollen and turbulent. Others are small and rocky, huddled close to their parent stars or drifting in the frozen dark. Statistically, there should be millions of worlds just like Earth, bathed in the warmth of a stable sun, with liquid water pooling on their surfaces and the chemical sparks of life igniting in their oceans. If the universe is a garden, it should be blooming. And yet, when we listen, we hear only silence. This is the heart of the Fermi paradox, named after the physicist Enrico Fermi. The story goes that during a casual lunch conversation about extraterrestrial life, Fermi simply asked, "Where is everybody?" It was a moment of clarity that cut through the optimism of statistical probability. If intelligent life is common, and if civilizations can spread across the stars, even at slow speeds, the galaxy should be humming with activity. We should see the signs of their engineering, hear the chatter of their communications, or perhaps even encounter their probes drifting through our own solar system. But we do not. We see a universe that is beautiful, majestic, and terrifyingly quiet. For more than half a century, astronomers have turned their radio telescopes toward the sky, scanning the frequencies for a signal, a pattern, a whisper that would tell us we are not alone. This effort, the search for extraterrestrial intelligence, or SETI, has been a vigil of patience and hope. Giant dishes like the one that once stood at Arecibo in Puerto Rico acted as vast ears cupped against the cosmic wind. They listened for a sequence of prime numbers, a burst of artificial pulses, or the faint leakage of a television broadcast from a neighbor star. We have listened to the nearest stars and the center of the galaxy. We have surveyed the sky across the electromagnetic spectrum. We have analyzed the light of distant stars for the telltale dip in brightness that might indicate a massive artificial structure passing in front of it. Occasionally, there have been moments of excitement. In 1977, a radio telescope in Ohio detected a strong, narrow-band radio signal coming from the direction of the constellation Sagittarius. It bore the hallmarks of an artificial origin. The astronomer who reviewed the data was so impressed that he wrote the word "wow" in the margin of the computer printout, but the signal never repeated. We turned our ears back to that spot in the sky, again and again, but there was nothing but the steady hiss of background radiation. It was a ghost, a fleeting anomaly that vanished as quickly as it appeared, leaving us to wonder if we had missed a greeting, or if we had simply been fooled by a passing comet or a secret military satellite. Other candidates have come and gone. We have seen stars that dim in strange, unpredictable patterns, leading some to speculate about alien megastructures, vast swarms of solar collectors built by advanced civilizations to harvest the energy of their suns. But upon closer inspection, the dust of the cosmos usually offers a simpler, more natural explanation. We find clouds of breaking comets, or disks of debris, or the chaotic pulsations of a variable star. The universe is full of noise, but it is the noise of physics, not of intelligence. It is the roar of exploding stars, the rhythmic pulse of neutron stars, and the ancient whisper of the Big Bang itself. It is a symphony of matter and energy, but it is a song without a singer. This silence is not just a lack of radio signals, it is a lack of physical evidence in a universe that is billions of years older than our solar system. The universe is approximately 13.8 billion years old. The Earth is only 4.5 billion years old. This means that there could be civilizations that had a head start of millions or even billions of years on us. Imagine what humanity might achieve in another 1,000 years or 1,000,000 years. We might learn to traverse the distances between the stars. We might build automated probes that can replicate themselves, spreading out across the galaxy like dandelion seeds, visiting every star system in the Milky Way within a few million years, a blink of an eye in cosmic time. If even one such civilization had arisen in the long history of our galaxy, their presence should be obvious. They would have had ample time to colonize, or at least explore the entire galaxy. We should see the infrared heat signatures of their industries, or the deliberate movement of stars, or the remnants of their past glories. Yet, we look out into the deep past and the deep distance, and we see a wilderness. The stars burn with the same nuclear fire they have fueled for eons, untouched and untamed. The galaxy appears to be in a natural state, pristine and wild, as if no one has ever touched it. This leads us to a sobering possibility, one that sits heavy in the stomach of anyone who ponders it deeply. Perhaps the math is wrong. Perhaps the optimist's view of the universe, the idea that life is inevitable and intelligence is a natural destination of evolution, is a misunderstanding of reality. We look at our own history, at the lush diversity of life on Earth, and we assume it is the norm. We assume that because it happened here, it must happen everywhere. But what if we are the exception? What if the silence is not a failure of our hearing, but a true reflection of an empty room? To understand why we might be alone, we must peel back the layers of our own existence. We must look at the chain of events that led to us, a chain that is long, fragile, and fraught with peril. It is easy to take our existence for granted. We wake up, we breathe the air, we feel the warmth of the sun, and it feels natural. But the more we learn about the universe, the more we realize that Earth is a rare jewel in a harsh and hostile void. The conditions that allow us to be here, thinking and wondering and listening, are the result of a delicate balance that may not exist anywhere else. Consider the environment of the universe itself. It is vast, cold, and filled with radiation. Most of the universe is a vacuum, a place where life as we know it would perish instantly. The islands of safety are few and far between, and even within those islands, the conditions must be perfect. We often talk about the Goldilocks zone, the region around a star where the temperature is just right for liquid water to exist. But the reality of a habitable planet goes far beyond just the distance from a sun. It involves the stability of the star itself, the protection of a magnetic field, the presence of a moon, the arrangement of giant planets, and a geological history that recycles carbon and keeps the atmosphere stable for billions of years. As we stare up at the Milky Way, we are looking at a graveyard of failed potential. We see stars that are too big and burn out too quickly for life to take hold. We see stars that are too small and volatile, lashing their planets with flares that would strip away atmospheres and sterilize surfaces. We see regions of the galaxy that are packed too tightly with stars, where the radiation from supernovae would scour any nearby worlds of life. We see systems where gas giants have migrated inward, swallowing up any rocky Earth-like planets in their path. The more we look, the more we see how many ways there are for a planet to remain dead. This perspective shifts the feeling of the night sky. The awe remains, but it is joined by a sense of profound preciousness. If we are indeed alone, or if intelligent neighbors are so rare that we will never meet them, then Earth is not just another planet. It is a lifeboat. It is a sanctuary in a dark and indifferent ocean. The silence of the universe amplifies the importance of the sounds we make here. The music, the languages, the laughter, the questions. It suggests that the phenomenon of consciousness, the ability of the universe to look at itself and understand itself, is incredibly fragile. We continue to search, of course. We build better telescopes, we launch more advanced probes, and we listen with greater sensitivity. We do this because the human spirit is driven by curiosity and the need for connection. To find even a single microbe on Mars, or a fossil in the ice of a moon like Europa, would tell us that life is not a miracle but a standard feature of the cosmos. But until that day comes, we must grapple with the data we have. And the data we have is a sky full of stars and a radio spectrum full of static. It is a heavy thought to imagine a galaxy where we are the only ones capable of looking up. It makes the universe feel vast and lonely. But there is also a strange beauty in it. If we are the first, or the only, then we are the custodians of meaning in the Milky Way. We are the storytellers. The stars may not have names given to them by others. They may only have the names we give them. The constellations may only be shapes drawn by human eyes. The silence is not necessarily a rejection. It may be an empty canvas waiting for us. As the night deepens and the earth turns, carrying us toward the dawn, the stars wheel overhead in their ancient silent dance. They do not care if we are watching. They burn and they fade, governed by the laws of gravity and fusion. But we care, we watch, we wonder. And in that act of wondering, we bring something unique to the cosmos. We bring a mind that tries to understand. The journey to understand our solitude requires us to look closer at the hurdles that any life form must clear. It is not enough to simply have a planet. The universe is filled with planets, but most of them are hellscapes of fire or ice. To find a world where the delicate chemistry of life can begin and then survive for the billions of years required to produce a radio telescope is a winning streak of cosmic proportions. We must examine the stars themselves, for they are the parents of planets, and not all parents are kind. We must look at the location of our home within the galaxy, for there are safe neighborhoods and there are war zones. We must look at the intricate dance of geology and biology that keeps a planet habitable. When we break down the requirements for a civilization to rise, the numbers begin to shrink. The billions of potential worlds become millions, then thousands, then perhaps just a handful. The silence begins to make sense. It is not that the universe is hiding its children. It is that raising a child to maturity in such a violent and chaotic cosmos is a task of immense difficulty. So, let us stand in the quiet of the dark, under the canopy of the infinite, and begin to unravel the reasons for the silence. Let us look at the gauntlet that life must run. It starts with the stars themselves, the nuclear furnaces that light the darkness. We often assume that any sun will do, but as we are about to see, the vast majority of stars in our universe are not creators of life, but destroyers of it. The stage is set, the curtain is drawn, and the audience is empty. To understand why, we must look at the nature of the galactic theater itself. To find a home in the vastness of the cosmos requires more than just a surface to stand on. It requires a sanctuary. When we think of the conditions for life, we often picture a warm pond, a gentle rain, or a sunbeam filtering through a canopy of leaves. But these are merely the final touches of a masterpiece that requires a very specific canvas and a very steady hand. Before biology can even begin to whisper its first secrets, the laws of astrophysics must carve out a safe harbor in a galaxy that is, by and large, a violent and inhospitable machine. We reside in the suburbs of the Milky Way. This is not a poetic metaphor, but a crucial survival factor. Our solar system sits in the Orion Arm, a quiet spur of stars located about 26,000 light-years from the galactic center. For a long time, astronomers believed that life could emerge almost anywhere within a galaxy, provided there was a star to warm it. But as we have mapped the structure of the Milky Way and measured the forces at play in its different regions, we have come to realize that real estate is everything. Just as a city has industrial zones filled with noise and pollution and quiet residential streets where families can grow, a galaxy has zones of death and zones of life. We are lucky enough to live in the latter, a region known as the galactic habitable zone. If we were to travel inward, toward the brilliant, crowded core of the galaxy, the night sky would be dazzling. The stars would be packed so tightly together that there might be no true night at all. But this beauty would come at a terrible cost. The galactic center is a chaotic, high-energy environment. Here, the density of stars is so high that close encounters between them are common. These gravitational tussles can disrupt the orbits of planets, sending them careening into the darkness or plunging them into their suns. It is a place of constant gravitational turmoil, where a solar system would struggle to maintain the stability needed for billions of years of evolution. But the danger in the core is not just gravitational, it is radioactive. The center of the galaxy is awash in intense radiation. It is home to the supermassive black hole Sagittarius A star, and swarms of neutron stars and white dwarfs. The frequency of supernovae, the explosive deaths of massive stars, is much higher here than in the suburbs. A supernova is a cataclysmic event that releases more energy in a few seconds than our sun will produce in its entire lifetime. If a star were to explode within 30 light years of Earth, the radiation would strip away our ozone layer, leaving the surface exposed to lethal ultraviolet light from the sun. In the crowded core of the Milky Way, these explosions happen with frightening regularity, effectively sterilizing distinct regions of space again and again. To live there would be to live in a perpetual bombardment where the delicate molecules of life are torn apart before they can ever assemble into something complex. Conversely, if we were to travel to the outer edges of the galaxy, to the lonely rim where the stars thin out into the void, we would face a different problem. It is safer there, certainly. The stars are far apart, and the skies are quiet. But the galaxy's outskirts are poor in the materials needed to build a world like Earth. The universe began with only hydrogen and helium. Every heavier element, the carbon in our cells, the iron in our blood, the silicon in our rocks, was forged in the hearts of dying stars. These elements, which astronomers call metals, are sprayed out into the galaxy when stars explode, enriching the gas clouds that give birth to the next generation of stars. The core of the galaxy is rich in these metals because so many stars have lived and died there. But the outer rim is chemically primitive. Out there, the gas clouds are still mostly hydrogen and helium. A star forming in the galactic outskirts might form gas giants like Jupiter or Saturn, but it would lack the material to build small, rocky planets with solid crusts and magnetic cores. Without a solid surface, there are no oceans. Without iron, there is no magnetic field to protect an atmosphere. The outer galaxy is a desert of gas, unable to construct the physical stages upon which the drama of life must be enacted. So, we find ourselves in the middle ground, the Goldilocks zone of the galaxy itself. We are far enough from the core to avoid the lethal radiation and the gravitational chaos, but close enough to the center to be rich in the heavy elements required to build rocky planets and biological beings. This specific ring of habitability is relatively narrow, and it immediately reduces the number of stars that could potentially host a civilization. The vast majority of the galaxy is either too dangerous or too empty. But finding the right neighborhood is only the first hurdle. We must also choose the right house. In this case, the house is the star itself. We often assume that our sun is a typical star, a standard yellow orb like billions of others. But the sun is actually quite special, and its stability is a rare gift. Most of the stars in the universe, about 75% of them, are red dwarfs. These are small, cool stars, burning their fuel so slowly that they can live for trillions of years. Because they are so common and so long-lived, astrobiologists once pinned their hopes on them. If life takes a long time to evolve, a star that shines for 1 trillion years seems like the perfect incubator. However, as we have studied these red dwarfs closer, we have found that they are temperamental parents. Red dwarfs are prone to violent tantrums. Because of their internal structure, they generate powerful magnetic fields that twist and snap, releasing flares of radiation that can be hundreds or thousands of times more powerful than anything our sun produces. A planet orbiting a red dwarf must be very close to the star to get enough heat to have liquid water, often closer than Mercury is to the sun. At this proximity, the planet is sitting in the firing line. When the star flares, the planet is blasted with X-rays and ultraviolet radiation. Over time, These flares can physically strip the atmosphere off a planet, boiling away its oceans and leaving it as a dry, irradiated rock. Furthermore, because these planets must huddle so close to their dim stars for warmth, they fall victim to a gravitational phenomenon known as tidal locking. Just as our moon always shows the same face to the Earth, a planet orbiting close to a red dwarf would likely become locked to its star. One side would face the star in a perpetual, scorching day, while the other would face the darkness in an eternal, frozen night. While it is theoretically possible for life to exist in the twilight zone between these two extremes, the atmospheric dynamics would be ferocious, with hurricane-force winds driven by the extreme temperature differences. It is a harsh, alien environment, far removed from the gentle cycles of day and night that regulate the biology of Earth. At the other end of the stellar spectrum are the massive blue giants. These stars are the celebrities of the galaxy, bright, hot, and impossible to ignore. But they are tragic figures. They burn through their nuclear fuel with ravenous intensity, shining with the light of thousands of suns. But they pay for this brilliance with their lives. A massive star might live for only a few million years before exploding as a supernova. In the context of evolution, a few million years is nothing. It took 4 billion years for simple life on Earth to evolve into humanity. A massive star would live, die, and incinerate its solar system before the first bacteria had even learned to replicate. These stars are not homes, they are fireworks. This leaves us with the yellow dwarfs, the G-type stars like our Sun. They are rare, making up less than 10% of the stars in the Milky Way. They are hot enough to keep a planet warm at a safe distance, allowing for a comfortable orbit where tidal locking is not an issue. They are large enough to have stable magnetic fields, avoiding the constant atmosphere-stripping flares of the red dwarfs. And crucially, they live long enough. A star like the Sun has a lifespan of about 10 billion years. This provides a long, stable epoch, a window of time deep enough for the slow, stumbling process of evolution to try, fail, and try again, eventually producing complexity. But even among yellow dwarfs, our Sun appears to be exceptionally well behaved. Astronomers have monitored other stars similar to ours and found that many of them are much more active, prone to super flares that could devastate a biosphere. Our Sun, by comparison, is sedate. It has been shining with a remarkably consistent output for billions of years. This consistency is the unsung hero of our existence. If the Sun's energy output varied by even a few percent over short time scales, Earth would swing wildly between ice ages and runaway greenhouse events. Instead, the Sun has provided a steady, reliable hearth fire, allowing the Earth's climate to remain within the narrow limits of habitability for eons. We must also consider the company our star keeps. More than half of the stars in the sky are not solitary. They are part of binary or multiple star systems. Imagine a sky with 2 suns. It is a staple of science fiction, beautiful and dramatic. But in reality, a binary star system is a gravitational nightmare for a planet. If the 2 stars are close together, a planet would have to orbit far away, where it might be too cold. If the stars are far apart, the planet might orbit one of them, but the gravity of the second star would constantly tug at it, stretching its orbit into an ellipse. This would cause the planet to endure extreme seasons, freezing as it swings away from its sun and roasting as it swings close. In many scenarios, the complex dance of gravity would simply eject the planet from the system entirely, casting it out into the frozen dark of interstellar space. Our Sun is solitary. It has no companion to disrupt the orbits of its planets. This isolation has allowed the solar system to settle into a flat, orderly disk, where the planets move in near-perfect circles. This circularity is vital. A circular orbit ensures that the amount of sunlight the Earth receives is constant throughout the year. If our orbit were more elliptical, like a comet's, we would not be here. The stability of our single, lonely star is the anchor that holds our world in the realm of the living. As we assemble these requirements, the vast numbers of the universe begin to feel slightly less overwhelming. We need a star that is in the right place in the galaxy, not too close to the dangerous core, not too far in the barren rim. We need a star that is the right mass, not too small and volatile, not too large and short-lived. We need a star that is solitary, ensuring stable planetary orbits. And we need a star that is exceptionally calm, even for its type. When we filter the galaxy through these sieves, the billions of potential homes dwindle. We are looking for a needle in a haystack, but the haystack is made of fire and radiation. The stability we enjoy on Earth, the reliable rise and set of a friendly sun, the predictable seasons, the atmosphere that clings to our planet because it hasn't been blasted away, these are not default settings. They are the result of a precise alignment of astrophysical circumstances. This realization brings a sense of vertigo. We are balanced on a tightrope. For 4.5 billion years, our solar system has avoided the major catastrophes that are common in the galaxy. We haven't wandered into a nebula that would choke the sun. We haven't passed close enough to another star to have our planet scattered. The sun hasn't hiccuped in a way that would sterilize the Earth. We have drifted through the spiral arms of the Milky Way, riding the waves of density and star formation, and somehow we have remained safe. The silence of the universe might be explained, in part, by the fact that quiet neighborhoods are hard to find. Civilizations may simply be unable to get a foothold in the more turbulent regions of space. Or perhaps they do rise, only to be wiped out when their star flares or a nearby supernova irradiates their world. The history of the galaxy may be a history of false starts, of little sparks of life igniting and then being snuffed out by the uncaring violence of physics. But we are here. Our star is steady. Our location is safe. The stage is set for the next great hurdle. Having a habitable planet is one thing. Sparking life from non-life is entirely another. The rock and the water and the sunlight are ready. But how does dead matter learn to live? The transition from chemistry to biology is perhaps the deepest mystery of all. A leap across a chasm so wide that we still do not know how it was crossed. As we turn our gaze from the stars down to the primordial soup of the early Earth, we confront the improbable nature of our own beginning. The Goldilocks zone provides the opportunity, but it does not provide the guarantee. We have secured a quiet street in the galaxy, and we have found a house that is warm and stable. But an empty house is not a home. For a planet to be more than just a wet rock orbiting a yellow star, something fundamental must change. The dead matter of the universe, the passive atoms of carbon and hydrogen that drift through the void, must somehow wake up. They must organize themselves into a structure that can take in energy, maintain itself against the chaos of entropy, and make copies of itself. This is the transition from chemistry to biology, and it is a threshold so mysterious and so profound that we still do not fully understand how it was crossed. Imagine the Earth 4 billion years ago. It is not the blue and green marble we know today. It is a world of violent contrasts. The sky is likely a hazy shade of orange or red, rich in carbon dioxide and methane, with no free oxygen to breathe. The oceans are vast, iron-rich, and possibly green, heated by the geothermal vents that bleed from the cracked crust and battered by tides far higher than any we see today, driven by a moon that orbits much closer to the Earth. It is a laboratory of global proportions, bubbling with the raw ingredients of life. In this primordial soup, atoms collided. They formed molecules, simple chains of organic compounds. We know this part is easy. We have found amino acids, the building blocks of proteins, inside meteorites that have fallen from space. The universe is actually quite good at making the spare parts for life, but having a pile of bricks is not the same as having a cathedral. The mystery lies in the assembly. How did these dumb, drifting molecules suddenly combine to form a code? How did they create a system that could store information and follow instructions? This event is known as abiogenesis, the origin of life from non-living matter. Despite decades of research, we have never been able to replicate this moment in a lab. We can create the conditions, we can mix the chemicals, and we can apply the sparks of energy. But we have never seen the spark of life ignite from scratch. It remains a black box in our understanding of history. We know there was a time when the Earth was sterile, and we know there was a time relatively soon after the planet cooled when it was teeming with microscopic life. But the bridge between those two eras is shrouded in fog. Some scientists argue that because life appeared so early in Earth's history, perhaps as soon as the surface was cool enough to hold liquid water, it must be easy. They suggest that life is a cosmic imperative, something that happens naturally whenever the conditions are right. If this is true, then the galaxy should be full of biology. Every wet rock should be coated in a layer of living slime. But there is another possibility, one that is far more unsettling. It is possible that abiogenesis is an incredibly unlikely event, a chemical lottery win so rare that it might happen only once in a galaxy, or perhaps only once in the entire visible universe. Even the simplest cell is a masterpiece of engineering. If we could shrink ourselves down and step inside a bacterium, we would not find a simple blob of jelly. We would find a bustling metropolis. We would see molecular machines ratcheting along cables, carrying cargo from one side of the cell to the other. We would see enzymes acting like scissors and glue, cutting and pasting molecules with terrifying precision. We would see the central library of the DNA, a long, twisted molecule containing the blueprints for the entire operation, being read and copied by armies of proteins. It is a factory of immense complexity, operating with a frantic, coordinated energy. To suggest that this just happened by the random jostling of molecules in a warm pond is, as one astronomer famously put it, like expecting a tornado to sweep through a junkyard and assemble a fully functioning Boeing 747. However, let us assume for a moment that the optimists are right. Let us assume that the galaxy is fertile and that simple single-celled life is common. If we traveled to 1,000 planets in the habitable zone, perhaps we would find 1,000 oceans filled with bacteria. But there is a second hurdle, a second great filter that looms even larger than the first. It is the leap from the simple to the complex. For the first 2 billion years of life on Earth, nothing much happened. The world was inhabited solely by prokaryotes, bacteria, and archaea. These are small, simple cells with no internal structure. They have no nucleus to hold their DNA, no mitochondria to generate power, and no complex organelles to perform specific tasks. They are efficient survivors, capable of living in boiling springs and deep underground rock. But they are limited. They are constrained by the laws of energy. A simple bacterium uses its outer membrane to generate energy. If it tries to get bigger, its volume increases much faster than its surface area. It simply cannot generate enough power to support a larger, more complex body. It hits a physical wall. This is exactly what we see in the fossil record. For billions of years, the Earth was a slime world. Evolution tinkered, certainly. It created new metabolic pathways, allowing life to eat sunlight, or sulfur, or iron. It covered the planet in microbial mats that transformed the atmosphere. But it never produced a plant, an animal, or a fungus. It never produced anything visible to the naked eye. The planet was stuck in a rut of simplicity. The bacteria were the masters of the world, but they were trapped in a technological stalemate, unable to grow, unable to build, unable to think. Then something miraculous happened. It was an event so singular and so strange that it appears to have happened only once in the entire 4.5 billion year history of our planet. It is known as endosymbiosis. Somewhere in the ancient oceans, roughly 2 billion years ago, a large single-celled organism, likely an archaean, engulfed a smaller bacterium. Usually, this is the end of the story. The big cell eats the little cell, digests it, and goes about its day. But on this specific day, in this specific drop of water, the digestion failed. The little bacterium survived inside the larger host, and instead of killing each other, they struck a deal. The little bacterium was really good at processing oxygen to create energy. It began to pay rent to its host by supplying it with excess energy. In exchange, the host provided protection and raw materials. This accidental partnership changed the rules of the game. The small internal bacterium eventually evolved into the mitochondrion, the powerhouse that drives every complex cell today. With this internal power plant, the host cell was no longer limited by its surface area. It could generate thousands of times more energy than a simple bacterium. It could afford to expand its library of genes. It could afford to build complex internal structures. It could afford to become a eukaryotic cell. This moment, the origin of the eukaryote, is the most critical turning point in the history of life. Every animal, every plant, every fungus, every algae, every living thing that you can see with your eyes is a descendant of that one singular merger. Without it, the Earth would still be a world of slime. We would not be here. There would be no trees to climb, no flowers to smell, and no brains to wonder about the stars. The implication for the search for extraterrestrial intelligence is profound. If this merger is difficult, if it relies on a 1 in a trillion chance encounter that must result in cooperation rather than digestion, then complex life might be vanishingly rare. We might be living in a universe where abiogenesis is common, where the stars are surrounded by living worlds. But those worlds are stalled. They are trapped in the long, boring era of the prokaryotes. A traveler visiting these planets would find oceans teeming with life, strange, colorful scums on the rocks, and perhaps atmospheric signatures of methane and oxygen. But they would find no forests, no coral reefs, no birds, and certainly no cities. They would find a galaxy of arrested development. This idea helps to explain the silence. When we listen for radio signals, we are listening for the product of a specific type of biological complexity. We are listening for a creature that has a large, energy-hungry brain, dexterous hands, and the social complexity to build civilizations. All of these traits require the high-energy budget that only complex eukaryotic cells can provide. A bacterium, no matter how much time you give it, will never build a radio telescope. It simply does not have the energy to run the genetic software required for intelligence. The gap between the simple and the complex is not just a matter of time, it is a matter of structure. On Earth, it took 2 billion years for that jump to happen. That is half the age of the planet. Half of the time available before the sun gets too hot and boils the oceans away was spent waiting for 2 cells to merge by mistake. This suggests that the transition is not inevitable. It is a bottleneck. It is a filter that stops the vast majority of life from ever becoming anything more than microscopic noise. We can see the difficulty of this leap by looking at how many times it didn't happen. Multicellularity, the idea of cells working together to build a body, has evolved independently dozens of times on Earth. Plants did it, animals did it, fungi did it, even some algae did it. Once you have the complex eukaryotic cell, building a body seems to be the next logical step. But the eukaryotic cell itself, that appears to have a single point of origin. All complex life on Earth shares the same internal machinery, the same DNA packaging, and the same mitochondria. It suggests that in 4 billion years, amidst a global ocean of experimenting bacteria, the door to complexity opened only once. If we look at the timeline of Earth, we realize how close we cut it. If that merger had taken twice as long to occur, 4 billion years instead of 2, it would have been too late. The sun is gradually getting brighter. In another billion years or so, it will be too hot for liquid water to exist on the surface of the Earth. The window for life is finite. If the transition to complexity is slow and difficult, many planets might run out of time before they ever produce an animal. They might spend their entire habitable lifespan as bacterial worlds, finally sterilizing into dead rocks without ever having hosted a creature that could look up and see the sun. This perspective paints a picture of a universe that is perhaps biologically rich, but intellectually poor. It is a universe of potential that is rarely realized. The silence we hear is the silence of the simple. It is the silence of worlds that never grew up. But even if a planet clears this hurdle, even if the lightning strikes and the cells merge and the oceans fill with fish and ferns, there is no guarantee that intelligence will follow. Evolution is a blind process. It does not aim for the stars. It aims for survival. It rewards the creature that can eat the most, breed the fastest, or hide the best. Intelligence is an expensive luxury. The human brain consumes 20% of the body's energy, despite being only 2% of its weight. For most species, in most environments, such an organ would be a liability, not an asset. We tend to view ourselves as the pinnacle of evolution, the inevitable destination of a ladder that leads upward. But nature is not a ladder. It is a branching tree. We are just one thin twig on a massive canopy. For hundreds of millions of years, the dinosaurs ruled the earth with brains the size of walnuts. They were perfectly adapted, masters of their domain. They did not need to build fires or write poetry to survive. If not for a cosmic accident, an asteroid impact that cleared the board, they might still be here, and we would not. So, the journey from dead matter to a listening mind is paved with improbabilities. We have the mystery of the first spark, the long stagnation of the simple cell, and the freak accident of the complex cell. And as we move forward in our story, we will see that the planet itself must play a role. It is not enough to have the biology. You need a world that challenges you without killing you. You need a world that is shaped by chance and catastrophe. A world where the moon, the neighbors, and the very crust beneath our feet conspire to keep the experiment running. The biological hurdles are steep, but the planetary ones are just as daunting. As we turn our attention to the physical history of the Earth, we will see that our planet is not just a passive stage. It is an active participant, a chaotic and violent partner that has, through a series of lucky breaks, sculpted the conditions necessary for us to exist. From the collision that gave us our moon to the shield of Jupiter, we are the beneficiaries of a cosmic winning streak that defies the odds. The story of life is a story of resilience, a fragile chemistry persisting against the odds. But resilience has its limits. Even the most robust cell, the most adaptable creature, needs a platform that endures. As we broaden our view from the microscopic dance of molecules to the grand architecture of our solar system, we discover that Earth is not merely a stage where the play of life happens to be set. It is a fortress built by a series of fortunate accidents and violent catastrophes that, by all rights, should have destroyed it. Instead, they sculpted it into the perfect cradle for a technological civilization. We often imagine that planets are static, unchanging objects, lumps of rock that simply spin and orbit for eternity. But the history of the Earth is one of profound violence. The very existence of our world as a habitable paradise is the result of a game of cosmic billiards played 4.5 billion years ago, a game where a difference of a few degrees in trajectory would have resulted in a barren, lifeless marble. Consider the moon. To us, it is a companion, a source of light in the darkness and a puller of tides. But to an astronomer, the moon is an anomaly. In our solar system, Mercury and Venus have no moons. Mars has 2, but they are tiny, captured asteroids that look more like dented potatoes than proper worlds. The gas giants have fleets of moons, but compared to the size of their parent planets, those moons are mere specks. Earth, however, possesses a moon of staggering size. It is 1/4 the diameter of the Earth itself. We are, in effect, a double planet system. This unique arrangement did not happen by the gentle accumulation of dust. It was born in fire. In the chaotic infancy of the solar system, when the Earth was just forming, a protoplanet roughly the size of Mars, which astronomers have named Theia, was on a collision course with us. It slammed into the young Earth with a force that defies human comprehension. The impact was so energetic that it liquefied the surface of our planet and blasted trillions of tons of molten rock into orbit. Over time, this ring of fire coalesced to form the moon. If this collision had been a head-on smash, Earth might have been shattered entirely, creating a new asteroid belt. If it had been a glancing blow, the debris might have escaped into space, leaving us alone. But the angle was just right to create a massive satellite. This matters for reasons that go far beyond the romantic glow of moonlight. The moon acts as a gravitational anchor. Planets are like spinning tops. They wobble. Over long periods, the gravitational tug of other planets can cause a world's axis to tilt wildly. Mars, for example, has no large moon to stabilize it. As a result, its axis has swung dramatically over its history, sometimes tipping over by as much as 60 degrees. This causes the climate to oscillate chaotically, with the poles becoming equatorial deserts and the equator freezing over. On a planet like that, life would constantly be chasing a stable climate, migrating thousands of kilometers every few million years just to survive. Earth, held steady by the moon's gravity, maintains a tilt of roughly 23.5 degrees. It wobbles slightly, but only within a narrow range. This stability gives us our seasons. It ensures that the equator remains warm and the poles remain cold. It creates the predictable long-term climate patterns that allow complex ecosystems to develop and flourish. Without the violent luck of the Theia impact, Earth might be a chaotic world of shifting ice caps and erratic weather, a place where evolution could never find a steady footing. But the moon does more than just steady our hand. It drives the tides. 4 billion years ago, when the moon was much closer to the Earth, the tides were colossal, scouring the land and pulling minerals into the sea. Many biologists believe that these intertidal zones, wet, then dry, then wet again, were the crucibles where the chemistry of life was concentrated and cooked. Even today, the tides mix the oceans, circulating nutrients and regulating the temperature. Without our silent silver partner, the oceans might be stagnant pools, far less capable of supporting a global biosphere. As we look further out into the dark, past the orbit of Mars and the rubble of the asteroid belt, we find another guardian, Jupiter. The sheer scale of Jupiter is hard to grasp. It is 2.5 times more massive than all the other planets in the solar system combined. Its gravity is the dominant force in our neighborhood, second only to the Sun. And for a long time we thought Jupiter was just a typical gas giant. But as we have discovered thousands of exoplanetary systems around other stars, we have learned that our solar system is actually quite strange. In many other star systems, we see gas giants that have migrated inward. They spiral closer and closer to their stars, becoming hot Jupiters. As these giants rampage through the inner system, they scatter the small rocky planets like bowling pins, ejecting them into interstellar space or pushing them into the star. If Jupiter had done this, Earth would not exist. We would have been swallowed or flung into the void billions of years ago. Instead, Jupiter stayed put, or rather, it danced a very specific dance. Some models suggest that Jupiter started to migrate inward, but was pulled back by the gravitational formation of Saturn. This grand tack cleared out the early debris of the solar system, pruning the population of dangerous asteroids and comets, but stopped short of destroying the Earth. Today, Jupiter acts as a shield. Its massive gravity well attracts comets and asteroids from the outer dark, either swallowing them whole or slinging them out of the solar system entirely. We saw this in real time in July of 1994, when the comet Shoemaker-Levy 9 broke apart and slammed into Jupiter. The explosions were visible from Earth. The scars in Jupiter's clouds were larger than our entire planet. If Jupiter were not there, or if it were smaller, the frequency of such impacts on Earth would be much higher. Instead of an extinction-level event every 100 million years, we might suffer one every 10 million years. Complex life would never have the time to recover and evolve intelligence before the next rock fell from the sky to reset the clock. Yet, protection from above is not enough. A planet must also be alive from within. One of the most critical and rare features of Earth is its geological activity, plate tectonics. We hate earthquakes and volcanoes. They are destructive and terrifying. But in the grand scheme of things, they are the heartbeat of the planet. They are the engine that keeps Earth habitable. Earth is the only planet in the solar system with active plate tectonics. The crust of our world is broken into giant slabs that float on the semi-molten mantle below. They grind against each other, dive beneath one another, and pull apart. This movement does something vital. It recycles carbon. Carbon dioxide is a greenhouse gas. It traps heat. If we had too much of it, we would end up like Venus, a hellscape with surface temperatures hot enough to melt lead. If we had too little, we would end up like Mars, a frozen desert. Earth has a built-in thermostat. When volcanoes erupt, they spew carbon dioxide into the atmosphere, warming the planet. When rain falls, it absorbs that carbon dioxide, turns it into weak acid, and dissolves rocks. This carbon is washed into the ocean, used by sea creatures to build shells, and eventually settles on the ocean floor. Over millions of years, the moving plates drag that ocean floor deep into the earth, where it melts, and the carbon is released again through volcanoes. This cycle regulates the temperature of the earth over millions of years. If the sun gets brighter, the rain falls harder, scrubbing more carbon out of the air and cooling the planet. If the earth gets too cold, the rain stops, volcanoes keep pumping out gas, and the planet warms up again. It is a self-correcting system that has kept liquid water on the surface of Earth for 4 billion years, despite the sun increasing its brightness by 30% in that time. Without this geological churn, Earth would have died long ago. Mars is a cautionary tale of what happens when the geology stops. Mars is smaller than Earth, so it cooled down faster. Its core solidified. When the core stopped moving, its magnetic field collapsed. Without a magnetic field to shield it, the solar wind, the stream of charged particles formed the sun, stripped away Mars' atmosphere and oceans, turning a warm, wet world into a freeze-dried husk. Earth's molten, spinning core generates a powerful magnetic field that extends far out into space, deflecting the solar wind and keeping our atmosphere safe. We are protected by a force field generated by the crushing heat beneath our feet. So, to get an Earth, you need a planet of the right size to keep its heat for billions of years. You need the right chemical mixture to allow for plate tectonics. Water specifically acts as a lubricant for the plates. You need a large moon to steady the axis, and you need a giant neighbor to catch the bullets. The list of requirements grows longer, but there is one final, ironic twist in the story of our planet. While we need stability to survive, we need catastrophe to evolve. If the Earth were too safe, nothing would ever change. Evolution is driven by pressure. It is driven by the need to adapt to new circumstances. 66 million years ago, the Earth was ruled by the dinosaurs. They had reigned for 150 million years. They were the masters of the planet, filling every niche. Mammals, our ancestors, were tiny, shrew-like creatures scurrying in the underbrush, hiding in burrows, active only at night. As long as the dinosaurs held the throne, there was no room for mammals to grow, to get smarter, to diversify. The path to intelligence was blocked by a ceiling of reptilian dominance. Then, a rock the size of a mountain, traveling at 20,000 kilometers per hour, struck the Yucatan Peninsula in modern-day Mexico. It was a singular, random event. If the asteroid had arrived 30 minutes later, the rotation of the Earth would have caused it to land in the deep ocean, potentially lessening the impact. Instead, it hit shallow water, rich in sulfur-bearing rocks. The explosion was millions of times more powerful than all the nuclear weapons on Earth combined. It vaporized the crust, sending a plume of molten rock and sulfur into the stratosphere. The sky turned to fire, then to ash, then to black. The photosynthesis stopped. The food chains collapsed. The dinosaurs, too large and hungry to survive the nuclear winter, vanished. But the mammals, small and adaptable, survived on seeds and roots in the dark. When the dust cleared, the world was empty. The throne was vacant. This catastrophe gave our ancestors the opening they needed. Over the next 60 million years, they grew in size and intelligence, eventually leading to the primates, and finally, to us. Without that asteroid, the dinosaurs might still be here today. There is no reason to believe they would have ever developed technology. They were perfectly successful without it. We are the children of the Chicxulub impact. We are here because of a bad day in the Cretaceous period. This role of chance is perhaps the most unsettling part of the equation. It suggests that intelligence is not the inevitable outcome of evolution, but an accidental byproduct of specific disasters. If you rewind the tape of life and play it again, you might get a planet of bacteria, or a planet of insects, or a planet of intelligent squid, or nothing at all. The sequence of events that led to us, the moon, the magnetic field, the plate, tectonics, the specific timing of extinction events, is a narrative so specific that it seems unlikely to be repeated often. We look at the other planets in our solar system, and we see the alternative histories. We see Venus, choked by its own atmosphere, a warning of a thermostat broken. We see Mars, rusted and dead, a warning of a planet too small to hold its shield. We see the battered face of the moon, a record of the violence we escaped. Earth is the survivor. It is the one that ran the gauntlet and emerged with its oceans liquid and its air breathable. This realization transforms our view of the ground beneath our feet. We are not just standing on dirt. We are standing on a miracle of geophysics. The stability we feel is an illusion, maintained by a dynamic engine of heat and rock that has been running for eons. The safety we enjoy is a gift from a gas giant hundreds of millions of kilometers away. The seasons we mark our years by are a gift from a collision that nearly destroyed the world. As we move toward the final hurdles, we must confront the nature of the mind itself. We have a habitable planet. We have complex life. We have a history that cleared the way for mammals. But is intelligence inevitable? Does a brain always learn to build a radio? Or is the human mind another fluke, an evolutionary experiment that is as rare as the planet that spawned it? The silence of the stars suggests that even when the stage is perfectly set, the actor may never arrive. We tend to tell the story of life as if it were a story of destiny. We look back at the fossil record, at the procession from simple sponges to fish, from fish to amphibians, from reptiles to mammals, and finally to us, and we see a straight line rising upward. In this version of the story, intelligence is the inevitable prize at the end of the game. We assume that if you give a planet enough time, and if you protect it from total destruction, it will eventually produce a creature that can build a library, compose a symphony, or launch a rocket. We believe that consciousness is the natural destination of biology, but nature does not care about our stories. When we look closely at the mechanics of evolution, we find that it is not an arrow pointing toward the stars. It is simply a reaction to the present moment. Evolution does not plan for the future. It does not save up its energy to build a better brain 1,000,000 years from now. It solves the immediate problem of survival with the most efficient tool available. And for the vast majority of life's history on Earth, the best tool for survival has not been intelligence. It has been speed, or armor, or venom, or the ability to reproduce by the millions. High intelligence, the kind that allows us to reflect on our own existence and manipulate the fundamental forces of nature, is not a default survival strategy. In fact, it is a dangerous biological gamble. To understand why, we only need to look at the economics of the body. The human brain is a demanding organ. It makes up only about 2% of our body weight, yet it consumes roughly 20% of our total energy. It is a furnace that must be constantly stoked. In a world where food is scarce and every calorie counts, having a brain like ours is a liability. If a famine strikes, the creature with the large, energy-hungry brain is the first to starve, while the creature with the small, efficient brain survives to breed another day. This is why, for billions of years, evolution has favored the mindless. The crocodile has remained virtually unchanged for 200 million years. It is a perfect killing machine with a brain the size of a thumb. It does not need to understand the stars to survive. It only needs to understand the riverbank and the ambush. The shark has patrolled the oceans for 400 million years, surviving mass extinctions that wiped out far more complex creatures. Bacteria, the simplest of all, are the true masters of the planet, outweighing all humanity and occupying every niche from the deepest trench to the highest cloud. These organisms are not primitive failures. They are spectacular successes. They prove that you do not need to be smart to endure. If intelligence were truly the most effective survival trait, we should see it everywhere. We call this concept convergent evolution. When a biological solution is truly excellent, nature invents it again and again, independently. The eye, for example, is such a useful tool that it has evolved separately dozens of times. Squids have eyes, eagles have eyes, flies have eyes. The details differ, but the solution is the same. Flight is another example. Insects evolved wings, dinosaurs evolved into birds with wings, and mammals evolved into bats with wings. The ability to move through the air is so advantageous that different lineages stumbled upon it independently. But when we look for technological intelligence, the kind that builds radios and civilizations, we see no convergence. We see a singularity. In the 4.5 billion years of Earth's history, among the billions of species that have lived and died, only one has ever developed the capacity to leave the planet. If the dinosaurs had a space program, all evidence of it has vanished. If the giant sloths built cities, they left no ruins. The silence of the fossil record matches the silence of the stars. It suggests that while eyes and wings are common solutions, high intelligence is a rare and specific adaptation, a winning lottery ticket that has been drawn only once. To understand how unlikely our existence is, we have to look at the bizarre chain of accidents that led to the human mind. It was not a smooth ascent. It was a stumble through a series of closing doors. It began with a change in the weather. Several million years ago, the lush rainforests of East Africa began to dry out. The dense canopy, which had provided a safe and easy home for our primate ancestors, began to fragment into patchy savanna. The apes that stayed in the shrinking forests remained apes. But one lineage was forced out into the tall grass. To survive in this new, dangerous environment, where predators lurked behind every bush, they had to stand up. Bipedalism, walking on two legs, was the first domino. It was efficient for covering long distances, and it allowed them to see over the grass. But most importantly, it freed their hands. For the first time, a creature had two limbs that were not needed for locomotion. They could be used to carry food, to hold children, and eventually to manipulate objects. This feedback loop between the hand and the brain is crucial. As our ancestors began to use stones to crack nuts and cut meat, the brain had a reason to get better at coordination, but a better brain needs more energy, and raw food is hard to digest. It takes a lot of time and energy to chew and process raw roots and meat. A primate can spend 6 hours a day just chewing. There is a ceiling to how big a brain can grow on a diet of raw food. Then came the Promethean moment, the control of fire. We do not know exactly when it happened, perhaps 1,000,000 years ago, perhaps more. But when our ancestors learned to cook their food, they outsourced their digestion. Cooking breaks down tough fibers and releases nutrients, making food far more energy-dense and easier to absorb. Suddenly, we could get the calories of a full day's foraging in a single hour. This surplus of energy went straight to the brain. We are the only animals that cook, and because of that, we are the only animals that could afford to grow a neuron-dense cortex capable of abstract thought. But even with big brains and free hands, we were almost wiped out. Genetic studies suggest that around 70,000 years ago, humanity passed through a severe bottleneck. The total population of our species may have dropped to as few as a few thousand breeding pairs. We were an endangered species clinging to the coastlines of Africa, one bad season away from extinction. If a virus or a drought had finished us off then, the Earth would likely still be a planet of apes and elephants today. The potential for radio telescopes would have died with that small band of survivors. We must also consider the specific type of intelligence required for a technological civilization. There are other intelligent creatures on Earth, but they are trapped by their biology or their environment. Consider the dolphin and the whale. They possess large, complex brains. They have language, culture, and deep emotional lives. In some ways, their social intelligence may rival our own. But they live in the water. You cannot build a fire underwater. You cannot smelt bronze or forge steel in the ocean. Without fire, there is no metallurgy. Without metallurgy, there is no electricity, no computer, no radio. A civilization of philosophers might swim in the oceans of a water world, singing complex songs to one another in the deep, but they will never build a transmitter to say hello to the stars. They are locked in a technological dead end. Similarly, we look at the octopus. It is an invertebrate genius, capable of solving puzzles, using tools, and escaping containment. It evolved intelligence completely separately from vertebrates. But the octopus has a fatal flaw. It has a very short lifespan. Most live only a year or two. They do not raise their young. The parents die before the eggs hatch. There is no transmission of knowledge from one generation to the next. Every octopus has to figure out the world from scratch. Civilization is, at its core, the accumulation of knowledge over time. Without the longevity to teach and the social structure to learn, intelligence remains a solitary parlor trick. This creates a sobering picture. To get a technological civilization, you need a creature that is not only smart, but one that has hands to manipulate the world, a terrestrial environment that allows for fire, a lifespan long enough to learn, and a social structure that encourages cooperation. And on top of all that, you need a planet that remains stable for the millions of years it takes for this specific combination to evolve. When we assume that aliens are out there, we are often guilty of what is called the planet of the apes fallacy. We imagine that if humans were wiped out, the chimpanzees would eventually evolve to take our place, developing speech and building. cities. But there is no evidence for this. If humans vanished tomorrow, the chimps would likely remain happily in the trees for the next 10 million years, just as they have for the last 10 million. Evolution is not trying to replace us. We are a fluke. This brings us back to the silence of the galaxy. It is possible that the universe is teeming with life, but that 99.9% of it is simple, single-celled slime. And of the fraction that becomes complex, 99% of that remains as animal-level intelligence. Herds of grazers, packs of hunters, swimmers in the deep, all living in harmony with their ecosystems, but none of them building a radio dish. Perhaps there are worlds where the dominant species is a hive mind of insects, incredibly efficient, but lacking the individual creativity to invent. Perhaps there are worlds covered in forests of thinking trees that communicate through fungal networks over centuries, moving too slowly to ever construct a machine. Perhaps the galaxy is full of poets and dreamers who lack the thumbs to build starships. The barrier of high intelligence suggests that we are looking for something incredibly specific. We are not just looking for life, we are looking for a mirror image of our own peculiar history. We are looking for a species that stumbled onto the same specific sequence of adaptations: bipedalism, tool use, fire, language, culture, that we did. And the more we understand our own past, the more it seems like a sequence that is unlikely to be repeated. There is a loneliness in this realization, but also a profound sense of responsibility. If intelligence is not a standard feature of the universe, but a rare and flickering candle in the dark, then our existence matters more than we can imagine. We are the universe's way of knowing itself. Without us, or beings like us, the cosmos is just a vast, beautiful, unobserved mechanism. It is a play with no audience. And yet, there is one final filter we must consider. Let us assume that against all odds, a species clears every hurdle. They find a safe star, a stable planet, and they survive the long road from bacteria to civilization. They discover science, they harness the atom, and they build the transmitters. What happens then? The silence might not be because civilizations never rise. It might be because they do not last. We look at our own history, a mere blip of a few thousand years of technology, and we see how close we have come to destroying ourselves. We have built weapons that can scour the life from our planet. We have changed the composition of our atmosphere. We have created technologies that evolve faster than our wisdom. This brings us to the concept of the Great Filter. It is the idea that there is some barrier in the timeline of life that is almost impossible to cross. The question that haunts us is the filter behind us, or is it ahead of us? If the filter is behind us, it means that the hardest part was the origin of life, or the origin of the complex cell, or the evolution of intelligence. It means we are one of the lucky few who made it, and the galaxy is empty because everyone else failed earlier in the game. In this scenario, we are lonely, but we are safe. We have already won the cosmic lottery. But if the filter is ahead of us, it means that rising civilizations are common, but they inevitably destroy themselves before they can spread to the stars. It means that the silence is not the silence of an empty room, but the silence of a graveyard. It suggests that technology itself contains a trap, a mechanism of self-destruction that is triggered whenever a society becomes powerful enough to change its world. As we look at our own precarious position, standing on the edge of the future with nuclear fire in our hands and the climate changing around us, we have to wonder, are we about to encounter the wall that stopped everyone else? Or are we the first to navigate these dangerous waters? The view from Earth is beautiful, but it is also terrifying. We are a species of soft, vulnerable creatures who have stumbled into the control room of a planet. We have learned to split the atom and read the code of life, but we still carry the aggressive tribal instincts of the savannah. We are a paradox, gods with the minds of apes. And as we stare out into the void, searching for a sign that we are not alone, we are really searching for a sign that it is possible to survive our own adolescence. The silence forces us to look in the mirror. It strips away the fantasy of a crowded Star Wars-style universe and leaves us with the stark reality of our isolation. It tells us that for all practical purposes, we are the only ones here. There is no galactic federation waiting to invite us in. There is no elder race coming to save us from our mistakes. We are on our own. This solitude is the final piece of the puzzle. It is the backdrop against which the human story is set. And as we move to our conclusion, we must ask, what does this mean for our future? If we are the solitary watchers of the Milky Way, what is our duty to this rare and fragile flame of consciousness? The silence is not just a scientific mystery, it is a call to action. It is a reminder that the future is not guaranteed, and that the continued existence of the only known mind in the universe rests entirely in our hands. If the silence of the night sky is a mirror, then the reflection we see is a test of our own maturity. We stand at a precipice, looking out into a void that refuses to answer us, and we are forced to decide what that silence means for our destiny. The concept of the Great Filter, that invisible barrier that prevents dead matter from becoming a star-faring civilization, is the most important riddle humanity has ever faced. It is not a riddle of mathematics or physics, but of survival. The answer determines whether we are the first to arrive at the party or the last to leave before the lights go out. Let us consider the possibility that the hardest part is already behind us. In this scenario, the Great Filter was one of the biological hurdles we have already discussed. Perhaps the origin of life is so incredibly rare that it has only happened here. Or perhaps the leap to complex cells is the stumbling block that stops almost everyone else. If this is true, then the galaxy is not a graveyard. It is an empty mansion waiting for its first inhabitants. It means that we are the solitary winners of a cosmic lottery, against odds so high that numbers lose their meaning. There is a profound loneliness in this view, but there is also a tremendous hope. It implies that there is no inevitable doom waiting for us in the future. There is no hidden trap in the laws of physics that destroys a civilization once it discovers radio or nuclear power. The path ahead is open. The stars are not barred to us. They are simply far away. If we can navigate the challenges of our own making, our tribalism, our environmental impact, our technological growing pains, then there is nothing stopping us from spreading life into the dead void. We could be the ancestors of a galactic civilization that will flourish for billions of years. We could be the ones who bring the universe to life. But there is the other possibility, the darker shadow that looms over the search for extraterrestrial intelligence. What if the filter is ahead of us? What if life starts easily, and intelligence evolves often, but civilizations are naturally unstable? This hypothesis suggests that there is something about the nature of technology and intelligence that leads to self-destruction. It is the idea that civilizations are like matches. They flare up brightly for a moment, illuminating the dark, and then they burn out. We can see the potential mechanisms for this burnout all around us. As technology advances, it becomes more powerful and more accessible. 1,000 years ago, a madman could burn down a village. Today, a small group of people could engineer a virus or trigger a conflict that unravels the global order. We are discovering technologies that have the power to rewrite biology, to alter the climate, and to create artificial minds that might outpace our own. It is possible that every civilization reaches this point, a bottleneck, where their power exceeds their wisdom and they fail to navigate it. They destroy their biosphere, or they unleash a weapon they cannot control, or they simply stagnate, retreating into virtual worlds of their own creation, losing the will to look outward. If the filter is ahead of us, then the silence of the night sky is a warning. It tells us that of all the civilizations that have reached our level of development, none have survived long enough to colonize the galaxy. It suggests that we are walking through a minefield that no one has ever crossed alive. However, we must be careful not to fall into despair. The inevitability of destruction is a hypothesis, not a fact. Just because others may have failed does not mean we must. We possess something that the dinosaurs did not, and that simple bacteria do not: the ability to foresee the future. We can model the climate. We can calculate the trajectories of asteroids. We can study the psychology of conflict. We are the first species on Earth capable of identifying the existential risks we face and choosing to avoid them. The filter may be formidable, but it is not a physical law. It is a challenge. Furthermore, we must reconsider our place in time. The universe is 13.8 billion years old, which seems ancient to us. But in the lifespan of stars, the universe is actually quite young. The era of star formation is far from over. The most common stars, the red dwarfs, will continue to burn for trillions of years. We have appeared at the very beginning of the cosmic story. It is entirely possible that we are the firstborn. Imagine a universe that is just waking up. For billions of years, the galaxies were chaotic, filled with exploding stars and radiation. Perhaps it has only recently become calm enough for complex life to flourish. We might be the first generation of intelligence to open our eyes. If this is true, then we will not find ruins or radio signals because the others have not arrived yet. We are the elder race. We are the ones who will set the tone for the future of the Milky Way. The silence is not an absence. It is a waiting. This perspective shifts the burden of meaning squarely onto our shoulders. If we are alone, then the earth is not just a resource to be consumed. It is a holy vessel. It is the only place in the observable universe where love, curiosity, art, and music exist. Without us, the universe reverts to being a mechanism of blind forces. A supernova is spectacular, but it is not beautiful unless there is an eye to see it and a mind to interpret it. A nebula is just a cloud of gas until we give it a name and weave it into our myths. We are the universe's way of feeling. This makes the preservation of our world the most important task in the history of time. Every species we allow to go extinct, every ecosystem we degrade, is a permanent loss to the universe's library of complexity. If we destroy ourselves, we do not just end the human story. We might be ending the only story that counts. We would be extinguishing the only light in the dark room. The stakes are infinite. This fragility is the strongest argument for why we must eventually leave our cradle. The Earth is fragile. It is vulnerable to asteroid impacts, to supervolcanoes, to the slow brightening of the sun. As long as humanity and the biological heritage of Earth is confined to a single planet, we are at risk. We are like a computer with no backup drive. A single glitch, a single bad day could wipe out everything. Colonizing other worlds, settling Mars, or building habitats in space is often framed as a quest for conquest or profit. But in the light of the Fermi paradox, it becomes a quest for insurance. It is about creating a backup of the biosphere. If we can establish independent branches of civilization, separated by the vast distances of space, we become much harder to extinguish. If one world falls, the others carry the torch. The silence of the universe urges us to spread out, not to conquer, but to survive. But let us return to the here and now, to the quiet of the earth beneath the stars. The question, are we alone, may not be answered in our lifetimes. We may continue to listen to the static for another 1,000 years. We may build telescopes the size of countries and see nothing but the glow of natural physics. And while that may feel disappointing to those of us who dream of contact, it should also make us feel incredibly, incredibly lucky. We are here, against all the odds, against the chaotic formation of the solar system, against the lethal radiation of the galaxy, against the difficult leap from dead matter to living cells, against the bottleneck of complex life, and against the rarity of intelligence. We are here. We are breathing. We are thinking. We are looking up. The atoms in your body were forged in the hearts of ancient stars that exploded long before the Earth was born. The water in your glass was delivered by comets from the frozen outer reaches of the solar system. The iron in your blood is the same iron that makes up the core of the planet, generating the magnetic field that shields you. You are not separate from the universe. You are a piece of it that has woken up. The silence of the cosmos is not a cold indifference. It is a space for us to fill. It is a quiet room in which we can hear our own heartbeat and the heartbeat of our planet. It teaches us that we do not need to look to the sky for salvation or for validation. We are the miracle we have been looking for. When you look at the moon tonight, remember the violence of its birth and be grateful for the steady hand it keeps on our shoulder. When you feel the warmth of the sun, remember the billions of other stars that are too angry or too short-lived to nurture a child, and be grateful for the calm brilliance of our yellow dwarf. When you see a tree, or a bird, or another human being, remember the billions of years of single-celled boredom that preceded us, and be grateful for the freak accident that allowed life to become complex. We are probably alone. The data points that way. The logic points that way. But instead of fear, let this knowledge fill you with a sense of preciousness. We are the custodians of the flame. In a universe of ice and fire, of vacuum and radiation, we are the keepers of the only known garden. So, as the night wraps around the world and the stars drift slowly across the sky, let the silence be a comfort. It is the sound of a universe that is vast, ancient, and peaceful. It is the sound of potential. We are the early risers, the first to wake in the long galactic morning. The day is just beginning, and the story is ours to write. Sleep well, solitary watchers. The stars are keeping you company, even if they cannot speak.